Movement through space is inevitable. You might not feel it, but right now you're sitting on a planet that is spinning on its axis, moving you at up to 1,600 kilometers per hour depending on your latitude. The Earth circles the Sun. The Sun moves through the Milky Way. The Milky Way moves through the local group of galaxies. And the local group moves through our local supercluster. And even that supercluster of galaxies is in motion, heading towards the Shapley supercluster, where scientists believe that there is a particularly large concentration of galaxies. I hope all this motion isn't making you too dizzy. But on the grandest scales of our universe, something strange is happening. Scientists have begun to realize that there is not enough mass in the Shapley supercluster to pull us towards it at the rate that we see. About 50% of the cause of that motion is unaccounted for. In 2017, researchers discovered a possible source for the rest of that motion. But it's not something pulling us, it's something pushing. I'm Alex McColgan and you're watching Astrum. Join with me today as we explore the evidence for the region of space known as the Dipole Repeller and try to understand how, in a universe filled with gravity, something can push us instead of pull. Let's start with a little context. It's taken a long time for astronomers to recognize that this motion was taking place. To understand that we were moving, scientists first had to make a map of the regions of space around us. And although we as a species have been mapping the stars since the beginnings of civilization, it was only thanks to Mr. Hubble in 1924 that we proved there are actually stars in other galaxies outside the Milky Way. Before then, although astronomers had seen fuzzy little clusters of light in the night sky that we now know to be galaxies, the common wisdom was that these were gas cloud spiral nebulae within the Milky Way, not something that existed beyond it. Hubble noticed several Cepheid stars, a type of variable star with a cycle of variation closely linked to their luminosity, within one such spiral nebula, and used the fact that this luminosity was very predictable based on distance to calculate very precisely how far away they were. Surprising many, he proved that they do exist beyond the Milky Way. Since then, astronomers have been scrambling to catch up with the new reality of galaxies and superclusters, and set about mapping the locations and distances to every galaxy they could find. Hubble had been studying Andromeda, our closest neighbouring major galaxy, but there were others. By the 1970s, Stephen Gregory, Lard Thompson, and William Tift definitively proved that galaxies didn't just float randomly in space, but converged into superclusters, large filamentary or sheet-like structures that exist between large bubbles of void. They mapped the first supercluster, the Coma supercluster, which covered a region of space 100 million light-years across. A whopping 95% of all galaxies are found in these superstructures. It wasn't until 2014 that our own supercluster, the Laniakea supercluster, was fully mapped. You might be surprised to hear it happened in that order. After all, wouldn't common sense say it's easier to map regions of space closer to us rather than ones further away? Why was it only nearly a century after the discovery of other galaxies existing, and 40 years after mapping the first supercluster, that we finally turned to our own? The answer is that mapping the local regions of space around us is surprisingly challenging, and it's all because of the Milky Way getting in the Milky Way. The Milky Way is full of gas and dust, and these regions are so difficult to penetrate that we can't really see beyond them. Towards the center of the Milky Way, this effect gets so bad that scientists have dubbed the whole area the zone of avoidance. Very little light gets through it. Not being able to see in this area is particularly relevant to our current discussion for reasons we'll get to later. In contrast to our local area, distant galaxies are easier to study, as all you have to do is point your telescope at a single point in the night sky and let it drink in the light. Mapping the area around us requires looking at every point in the night sky. It's proved quite difficult, although astronomers are now getting a better handle on it. Thanks to their efforts in looking at thousands of galaxies in our galactic neighborhood, and by studying galaxies' peculiar motion, or their motion relative to the cosmic background radiation that ignores the expansion of the universe, scientists have been able to group gravitationally bound galaxies into superclusters. At the center of our Laniakea supercluster lies a point known as the Great Attractor, an area 150 to 250 million light years away from us, that we, in the Milky Way, are slowly drifting towards. Sadly, the Great Attractor lies within the zone of avoidance, so it's tricky to see clearly what lies there. To confound things further, the Laniakea supercluster was also found to be moving. It travels towards another supercluster known as the Shapley supercluster, taking us along with it. At the center of this supercluster lies the Shapley Attractor, which also is believed to be incredibly dense in terms of mass. But frustratingly, this second attractor also lies in the zone of avoidance, making it difficult to see exactly what's going on over there too. Thankfully, as X-ray and infrared telescopes improved, it became possible to take a better look at these two attractors. But this is where the mystery begins. What mass is there is not quite massive enough to account for our apparent motion in that direction, which is why a team of researchers from the University of Hawaii published an article in Nature to attempt to explain this discrepancy. The team was made up of Yehuda Hoffman, Daniel Homerede, R. Brent Tully, and Helene M. Courtois. Together they created a new kind of map of the local universe around us. This time, instead of simply noting galaxies' positions, they highlighted their motions instead. This allowed them to create a map of flow lines, which, after mathematical analysis, allowed them to make assumptions about the locations of masses in our nearby superclusters. Their results were surprising. A lot of our local mass is moving towards the Shapley supercluster, which is what you would expect. But they also found a lot of mass is moving away from another specific region in space. They call this mystery patch of space the Dipole Repeller. Together, the Dipole Repeller and the Shapley Attractor both contribute about 50% to our motion, working together in tandem, hence the name dipole. But how? Gravity is a force that, so far as we have observed, only pulls. What lies in this region of space that allows a push to happen? Could it be a strange collection of white holes? The theoretical opposite of black holes that we've talked about in videos before? Or perhaps some source of anti-gravity? Not quite. The answer is nothing. The Dipole Repeller is a void, a bubble about 100 million light years across that does not contain many, if any, major galaxies. It's one of the bubbles that exist between the filaments of the universe's structures. But interestingly, our galaxy's current motion lines up much more satisfyingly with the push from this region than it does from the pull of the Shapley Attractor, which is a compelling argument in this theory's favor. So, how does nothing push? The answer is actually that this could be a pseudo-force more than it is a real one. Imagine a universe where all the galaxies were spaced equally. While the gravity of galaxies above would pull you, the gravity of galaxies below you would do the same. So would the pull of galaxies to your left and to your right. In this way, the varying forces of all these gravities would balance each other, leaving you to not really travel in any direction. You'd be in a perfect equilibrium. But what would happen if we removed the galaxies from one of these directions? What would happen if we added a void? Well, then the scales would tip. There would be one direction that no longer pulled you, leaving the opposite direction's pull to act on you unimpeded. As a result, you would move away from the void as if it were pushing you. Everything near a void will thus move away from it, making it seem to have a repelling gravitational force. It is something of an optical illusion. There is another explanation for why a void space might push you, which might work in tandem with the pseudo-force. The universe is expanding, and that expansion shows no sign of slowing down. In fact, it seems to be speeding up. However, this expansion is counteracted by gravity, and in areas where there is more gravity, less expansion seems to take place. Stars aren't just being pushed away from each other, they're also being pulled together. Conversely, in a void, there is nothing to contain this rampant expansion. As a result, void spaces literally will swell compared to their supercluster counterparts. It might be done by warping the fabric of reality, but this also achieves a sort of push. Since 2017, not much more has come to light about the existence of the dipole repeller. As this is still an expanding field of research, there's some debate about whether it's really there, or how influential it might be on our galaxy's current motion. It is difficult to observe due to the Milky Way's obscuring effect, and there is always a challenge inherent in trying to spot the absence of a thing rather than its presence. However, Tully and his fellow researchers hope that with the aid of future ultra-sensitive surveys in multiple spectrums of light, it will be possible to map out the few galaxies that lie in this void, and generally confirm its existence in the region they hypothesize. We are constantly moving through space, but even the science of space is always in motion. Each new galaxy, along with data regarding its redshift and travel speed, helps us develop a broader understanding of the movement of the galaxy. It's fascinating to think that not all of that motion is caused by the pull of gravity. It might turn out that sometimes the universe just needs a little push to get going. There have been a lot of awesome images in the Astrum videos over the years. Sometimes the visuals we show in our videos are so colourful, so grand and so awe-inspiring that the short 3-second clip doesn't really do them justice. In those cases, I felt it would be really cool if there was a way to come back to these images again and again, to relive the magic of those moments, and to capture the power and enormity of space. To that end, I've spent the last couple of months working with artists to develop 70 by 50 centimeter posters that captures those epic moments. We've created a set of premium prints that look great and act as a daily reminder of the universe that surrounds us. Perfect for bringing grandeur to your wall, or as an inspiring motif in your office space. Follow the link electrify.art/Astrum to check them out, and do let me know what you think of them actually in the comments below.